In this talk, I will go through some novel ideas on 6G wireless networks. I chose three topics among many 6G research directions: intelligent surfaces, satellites, and blockchains. Uh, when the communication links between the transmitters and receivers are blocked, as seen in this figure. So here receiver 2 is blocked. Intelligent surfaces can aid us in creating an alternative link for this blocked connection. I'll put my laser point. When the transmitter transmits a signal, the intelligent surface, I chose a brief name, there are many names as you know in the literature, can reflect this received signal towards the receivers. So here now receiver 2 is reachable by transmitter 1. Also the communication between transmitter 1 and receiver 1 is improved due to the extra connection. These are called reflecting elements since they reflect the incoming signals. So there are many survey papers on intelligent surfaces. The first question that we ask to ourselves, what is the difference between intelligent surfaces, IS networks versus relay networks, or why don't we use massive MIMO instead of intelligent surfaces? Are there different types of surfaces? I will not go through these details due to the time limitation. There are many challenges in this IS network topic. Two of them are channel estimation and feedback. There are quite some number of publications on channel estimation. I haven't carefully looked, but when I quickly overview, I could see only two publications on feedback. Feedback is also important as channel estimation. So channel estimation can be more challenging. For instance, intelligent surfaces are not capable of transmitting pilot signals, and intelligent surfaces introduce many extra channel coefficients to be estimated. So these are some of the challenges I introduce. So our proposal to relieve this burden, channel estimation burden or feedback burden, is network sparsification. We can put sparsity constraints in the optimization problem we would like to solve. For instance, if we have an uplink communication and we pairs transmitter 1 and receiver 1, we pair transmitter 2 and receiver 2, that is transmitter 2 wants to transmit to receiver 2 but not to receiver 1. So shall we pair with a receiver 3 with one of the transmitters? When we introduce the sparsity constraint, maybe it will decide that receiver 3 should be shut off, because let's say we pair transmitter 1 and receiver 3, then in this case transmitter 2, as you see in the setup, might cause too many interference on receiver 3. So the sum rate gain by including receiver 3 might be marginal considering the backhaul load. Here I forgot to mention that the goal is to do centralized channel estimation, for instance. But when we consider the many multiple users, transmitters, many IS in the network, this backhaul might be overloaded. So we might want to sparsify our network by eliminating some receivers. In the downlink, for instance, we can eliminate some of the intelligent surfaces. If transmitter I wants to communicate to receiver I, perhaps these two ISs, intelligent surfaces, might be eliminated at the end of solving this optimization problem, because for instance transmitter 1, if this intelligent surface is not eliminated, transmitter 1 might cause too many interference on receiver 2, or similarly transmitter 2 might cause through this link to receiver 1 too many interference on receiver 1, so we can do such elimination. That is to be explicit. For instance, as an example, the sum rate loss due to excluding some network nodes, either receivers, transmitters, or intelligent surfaces, might be marginal compared to the reduction of feedback load. So this is one of our proposals. So there can be inherent sparsity in intelligent surface networks when we work in high frequency bands such as millimeter wave and terahertz bands. So intelligent surfaces can help in these frequency bands to relieve the high propagation losses. And in these frequency bands, the sparsity of the channel already exists in the frequency delay and angle domains. So then for these cases and the previous two slides I mentioned, we can explore compressed sensing techniques. Here is a short link that I tried to explain in a YouTube video very casually, kind of an introduction to compressed sensing techniques. The other scenario, I thought, satellites and 6G networks can be fully integrated. Low Earth orbit satellites are very popular, such as cube satellites. These are small units, although I have a large satellite here. They are small, cost-effective units. So as you know, the conventional scheme is if the user is getting far from the network coverage, the base station might ask satellite to step in to aid for this user to keep receiving the quality of service that 6G network offers. And there can be due to the synergy between satellite networks and low Earth orbit satellite networks and 6G networks, there can be new services. For now, when we want to track the tracks, we basically track via GPS, and we see the location of the track as a simple dot on a map. Perhaps we can see the live video or live photo transmission on our smart devices instead of seeing just a simple dot on our screen. This kind of service can be utilized for all kind of business directions, even among family members. So then satellite communications will enrich the services that 6G can offer. Another research direction can be the security problem in IoT, Internet of Things, in 6G networks. It is a very important problem, and blockchain can help in securing the 6G. I try to explain here briefly. Blockchain is a growing list of transaction records or growing list of blocks that make up the blockchain, because these blocks are linked to each other. If user A makes a transaction to user B, this can be a wireless transmission, a cryptocurrency, or a digital signature. A block is added to the chain. If user B transmits to user C, makes another transaction to user C, the block is again added. Since these blocks are closely connected to each other, it's not easy to tamper these blocks. The basic idea here is, for instance, block 2 has a content, and it will have a hash number for block 2 based on the content and based on the hash number that belongs to the previous block. So this is repeated as blocks are added. So when the content of n-1th block wants to be changed, such as the amount of currency, or some intruder is in the wireless network and wants to get some data, the content will change and its hash number will change. So this hash number will affect the next block, as you see here, n-1. So the intruder must tamper all consecutive blocks so that this tampering won't be detected. Right now we have many high power computational powers. There are two more elements that make this impossible for intruders to tamper all the blocks. They are called proof of work and consensus. So a block can be added into the blockchain in some time, such as 10 minutes in Bitcoin case. So it takes a while. So since all blocks are keeping edited, it will be nearly impossible to tamper all blocks. And the second element is consensus. So at the end of the proposal that the block needs to be added to the blockchain, users will verify, independent users, peer-to-peer network will verify this transaction, and when the consensus is reached, the block will be decided to be added to the blockchain. And then in this case, the intruder must somehow dominate the peer-to-peer network so that 51% of consensus is decided falsely. So this is also nearly impossible. So how can this be achieved in wireless networks, IoT networks? We can benefit from edge networks. So by offloading these heavy computations on edge and cloud networks, and by adjusting the parameters for wireless networks, such as not 10 minutes, but some intervals. Also, the block can be added at some intervals of transmissions, not at every transmission. This security can be improved. So as a use case, a couple of years ago, FCC, Federal Communications Commission of US, mentioned that spectrum sharing can be done via blockchain. In our work, we proposed a relay selection for transmit power minimization. There can be some extra relays in the network. We can call them blockchain relays. So these blockchain relays, when they are idle, they can notify the network, and then users, if they want to, can compete for these extra relays, blockchain relays, to improve their communication rates. So users have two important parameters: power consumption and reg coins, which can be called relay coins. So there will be an optimization problem here. So this can be one way of introducing blockchains in wireless networks. And actually, my talk is very short.